Hi, I'm Bob. We will continue our solutions to the exercises in section 7.3 about the long-run costs, when the firm can vary both the labor and the capital inputs. I used the textbook Microeconomics Theory and Applications with Calculus, the 5th edition by Professor Jeffrey Perloff. Let's solve exercise 3.7. Replace the production function in solved problem 7.4 with a Cobb-Douglas form and use calculus to find the cost-minimizing capital-labor ratio. We use the shortcut method to find the cost-minimizing capital-labor ratio. The shortcut method uses the fact that if there is an interior solution to the minimization problem, the isoquant is tangent to the isocost line at the cost-minimizing combination of the inputs. By the tangency rule, the factor price ratio equals the marginal product ratio. The former is the slope of the isocost, and the latter is the slope of the isoquant. We obtain the answer. The capital-labor ratio equals B over A times W over R. For example, if the wage rate and the capital price are both 1, then the capital-labor ratio equals B over A. If A equals B, then capital equals labor. If the firm produces 4 units of output and we set the parameters equal to 1, then the firm uses 2 units of labor and 2 units of capital to minimize its cost. Let's find answers to exercise 3.8. Derive the long-run cost function for the constant elasticity of substitution production function. We use the same method as in the last video to derive the long-run cost function in 3 steps. In the first step, we find the expansion path equation, in which we express capital in terms of labor. In the second step, we express labor and capital in terms of output. We use the production function and plug in the expansion path equation to write output Q as a function of labor L. Then we write the inverse function to express labor in terms of output. Plugging labor into the expansion path equation gives the capital function in terms of output. Now we have both inputs in terms of output. In the third step, substituting labor and capital into the cost identity gives the long-run cost function. Let's solve exercise 3.9. For Cobb-Douglas production function, how does the expansion path change if the wage increases while the rental rate of capital stays the same? For Cobb-Douglas production function, we use the tangency rule to find the expansion path equation. The slope of the isocost lines is W over R. The slope of the isoquant is the marginal product ratio. At the tangency point, the two slopes are identical. We obtain the expansion path equation. The slope of the expansion path is B over A times W over R. If the wage rate increases while holding the rental rate of capital fixed, the slope goes up. The expansion path becomes steeper. If the wage rate decreases, the expansion path becomes flatter. We can draw a graph to show how the expansion path changes with the factor price ratio. A lower price ratio results in a flatter expansion path. Let's go to exercise 3.10. The bouncing ball ping pong company sells table tennis sets, which include 2 paddles and 1 net. What is the firm's long-run expansion path if it incurs no costs other than what it pays for paddles and nets, which it buys at market prices? How does its expansion path depend on the relative prices of paddles and nets? The paddles and the nets are perfect complement inputs. The firm uses them in a fixed proportion. The isoquants are right angles for perfect complement inputs. By the lowest isocost rule, the cost minimizing combination of the inputs for a given level of output is at the point where the lowest isocost line touches the isoquant. The slope of the isocost lines is the relative price of paddles to nets. As the relative price falls, the isocost lines become flatter, but the cost minimizing bundles of inputs are unchanged by the lowest isocost rule. As a result, the expansion path is not affected by the relative price change. It is a straight line with a slope of 1 over 2. Let's solve exercise 3.11. Suppose that your firm's production function has constant returns to scale. What is the long-run expansion path? This exercise concerns the relationship between the returns to scale and the expansion path. We consider a Cobb-Douglas production function. From previous exercises, we know that if A plus B equals 1, then the production function exhibits constant returns to scale. If A plus B is greater than 1, then the production function exhibits increasing returns to scale. If A plus B is less than 1, then the production function has decreasing returns to scale. The degrees of returns to scale depend on the parameters A and B. On the other hand, the tangency rule for the cost-minimizing combinations of inputs leads to the expansion path equation. If the parameters A and B and the factor prices W and R are given, the expansion path is a straight line, regardless of the production's returns to scale. It does not depend on the sum of the parameters A and B. This example illustrates that the expansion path is a straight line if the production function has constant returns to scale, but it is still a straight line for increasing or decreasing returns to scale. Let's do exercise 3.12. A production function is homogeneous of degree g and involves three inputs L, K, and M. The corresponding factor prices are W, R, and E. Derive the long-run cost function. Please check out exercises 3.6 and 3.8 for the steps to derive the cost function from a production function in a Cobb-Douglas form or a constant elasticity of substitution form. If we want to find out the relationship between the cost function and the production function's degree of returns to scale, we can use Euler's theorem on homogeneous functions to connect them. First, we write the Lagrangian problem. We minimize the cost to produce a given level of output. The first three first-order conditions provide expressions on the factor prices. Then we write the cost identity and substitute for the factor prices. We find that the second term is part of Euler's theorem on homogeneous functions. If the production function is homogeneous of degree g, then the marginal product of labor times labor plus the marginal product of capital times capital plus the marginal product of materials times materials equals g times the production function. As a result, the cost function can be written as lambda times g times f, where lambda is the marginal cost of output, g is the degree of returns to scale, and f is the production function. This equation relates the long-run cost function to the production function and the degree of returns to scale. Thank you very much for doing the exercises with me today. If it helps, please subscribe to my YouTube channel. See you tomorrow in the last part of this section. Thank you for watching this video and subscribing to my YouTube channel. See you next time.